World 7 shows why semiconductor careers do not end at the edge of the silicon. System software, firmware, equipment control, factory software, semiconductor data, and AI, EDA development, design enablement, and customer engineering all determine whether hardware capability becomes usable value. These roles are expanding as chips become more heterogeneous, factories become more automated, and engineering workflows become more computational. This world is particularly relevant for computer science and software-oriented students who may not initially see a place for themselves in semiconductors. The opportunity is real, but domain knowledge still matters. The strongest engineers understand both the software system and the physical or design problem that software is helping to solve. System and chip software makes complex silicon usable. Drivers, runtime layers, operating system integration, compilers, libraries, and platform software translate hardware capability into something applications can actually exploit. As chips become more heterogeneous, software increasingly determines whether accelerators, memory systems, and interfaces deliver their promised value. Engineers in this mission need enough hardware understanding to reason about registers, interrupts, memory movement, concurrency, and performance, while also writing robust software. A strong project might integrate a custom hardware block with a driver and application, then measure end-to-end behavior rather than stopping at isolated hardware or software functionality. Firmware and embedded software operate close to the hardware and often control the earliest moments of system life. Boot sequences, device initialization, power management, calibration, security functions, and real-time control all depend on firmware that must behave predictably under tight resource constraints. The work rewards engineers who are comfortable moving between registers, protocols, timing, C or assembly, and hardware debug. A strong student project should demonstrate real interaction with hardware, for example, bringing up a peripheral, handling interrupts, implementing a boot or control sequence, and documenting how software behavior was verified against the underlying hardware. Equipment and control software gives semiconductor tools their operational intelligence. Motion control, recipe execution, sensor acquisition, interlocks, sequencing, fault handling, and user interfaces must coordinate complex physical subsystems safely and deterministically. Increasingly, this software also interfaces with advanced control algorithms and data systems. The mission is distinct from general factory software because the control loop is tied directly to a specific machine and process. Students can build relevant evidence with a hardware-in-the-loop controller, state machine-based equipment sequence, or real-time control application that demonstrates safe transitions, fault recovery, and measurable control performance. Manufacturing and factory software coordinates information and decisions across the production environment. MES, dispatching, scheduling, traceability, automation, equipment interfaces, and data services allow thousands of process steps and assets to operate as a coherent factory. The challenge is reliability at scale. Software errors can disrupt physical production, while poor scheduling can waste expensive capacity. This mission is increasingly important as fabs and assembly test factories pursue higher automation and more data-driven control. A strong student project might model dispatching policies, build a traceability workflow, or integrate equipment data into a production decision system. The value lies in connecting software behavior to measurable factory outcomes. Semiconductor data and AI engineering applies analytics and machine learning to engineering data whose physical meaning matters. Wafer maps, sensor traces, inspection images, test results, process histories, and equipment logs are not generic datasets. Each reflects a manufacturing or product mechanism. Successful engineers therefore combine data methods with domain understanding, careful validation, and attention to false correlations. Opportunities are expanding in defect classification, predictive maintenance, process optimization, yield learning, and intelligent equipment. A strong portfolio should show more than model accuracy. It should explain the engineering question, data provenance, validation method, and how the result could support a real decision. EDA and computational engineering builds the algorithms and software engines that make chip design tractable. Placement, routing, timing analysis, simulation, verification, extraction optimization, and numerical solvers all require scalable computation over extremely large problem spaces. This mission is not simply using an EDA tool, it is creating the computational methods behind such tools. It attracts engineers who enjoy algorithms, graph problems, optimization, numerical methods, parallel computing, and software performance. A strong student project can be modest in scale but should expose the core reasoning, for example, a placement heuristic, timing analyzer, simulator, or optimization engine whose accuracy and computational behavior are measured rather than assumed. Design enablement, PDK, and IP engineering connects manufacturing technology to the designers who need to use it. A process is not commercially useful merely because transistors can be fabricated. Designers need models, design rules, libraries, IP, reference flows, verification collateral, and correlation to silicon. Engineers in this mission translate process capability into a dependable design ecosystem and work across foundry, EDA, IP, and customer teams. The mission is especially important at advanced nodes and in heterogeneous integration, where design rules and interfaces are increasingly complex. Strong evidence can include model-to-measurement correlation, library or IP characterization, or a reproducible design flow that demonstrates first-time right behavior. Applications in customer engineering is where deep technical knowledge meets a customer's real design or manufacturing problem. These engineers help customers evaluate technology, integrate products, debug issues, optimize flows, and close technical gaps that cannot be solved by documentation alone. The role is not simply sales support credibility, depends on understanding the product well enough to reproduce problems and propose defensible solutions. It also provides a valuable feedback path into product and R&D teams. Students can prepare by documenting a technically demanding integration project as though another engineering team were the customer-defined requirements, reproduce issues, explain trade-offs, and demonstrate closure with evidence. This connection map is where the 35 missions become a system. No mission produces value in isolation. Architecture creates targets that design teams implement. Design and process choices constrain packaging manufacturing data flows into yield and quality product behavior, feeds back into design, process, and test software, and customer engineering turn hardware capability into usable solutions. The arrows should be read as engineering dependencies, not as a rigid organizational chart. In a real company, reporting lines may differ, but the technical handoffs remain. When evaluating a career, look at both the mission you may join and the missions that consume or influence its output. Part 3 changes the question from "What does this engineer do?" to "Who owns the decisions inside a real product?" HBM is a useful example because it combines memory architecture, high-density interconnect, package integration, thermal and mechanical constraints, test, yield, reliability, and system-level performance. The point is not to teach HBM design in a few slides. It is to demonstrate a method for reading any semiconductor product. Once you learn to identify the major technical decisions and trade-offs, you can map those decisions back to the missions and see where different engineering careers contribute. Suppose you say, "I want to work on HBM." That is a good starting interest, but HBM is not one job. It is a product ecosystem containing many engineering problems. One engineer may work on memory architecture, another on die design, another on TSV or bonding processes, another on package power integrity, another on thermal behavior, test, yield, reliability, or customer integration. Career exploration becomes much more concrete when you replace the product name with the decision you want to own. The useful next question is therefore, which part of HBM do I want to understand deeply enough to make engineering decisions about it? This slide assigns ownership to decisions rather than to titles. That distinction is valuable because complex products create shared boundaries. An architecture team may define bandwidth and capacity targets, but package and signal integrity teams determine whether the physical interconnect can support them. Process teams establish manufacturability, while test and yield teams reveal whether the resulting product can be produced economically. Reliability teams evaluate whether it will survive the required lifetime. No single team owns the entire product, yet each team owns a decision that others depend on. This is a useful model for interviews as well describe the engineering decision you can contribute to, not merely the tool you have used. The decisions in an advanced semiconductor product are coupled. Increasing bandwidth can raise power density. Denser integration can make thermal paths more difficult. A package change can affect signal integrity, warpage, assembly yield, test access, and reliability. A process improvement can introduce a new material or stress condition elsewhere. This is why strong semiconductor engineering often involves trade-off reasoning rather than local optimization. When you build a project, try to expose at least one such trade-off. A project becomes more credible when you can explain not only what improved, but what constraint became more difficult and how you evaluated the balance. The HBM example is only a template. You can apply the same reading method to an AI accelerator, image sensor, automotive SoC, RF transceiver, power device, advanced node CPU, or chiplet system. Start with the product requirements. Identify the major technical decisions. Map each decision to the engineering mission that owns it, then trace the dependencies among those missions. This approach helps you move beyond brand names and fashionable technologies. Even when the product changes, the underlying questions, architecture, implementation, manufacturing, integration, validation, reliability, software, and customer use, remain recognizable. That is what makes the mission framework reusable. Before comparing employers, we group companies by business model because the business model changes which engineering missions are most visible. A fabless company concentrates heavily on architecture, design, verification, software, and product realization through manufacturing partners. An IDM combines design with internal manufacturing. A foundry emphasizes process technology, manufacturing, enablement, and customer integration. Equipment companies build the tools and control technologies behind manufacturing. EDA companies create computational design infrastructure. OSAT companies specialize in packaging, assembly, and test. These are tendencies rather than rigid rules, but they provide a useful lens for interpreting published roles. Part 4 examines company types using published role information. The objective is not to infer hidden organizational structures or to rank employers. It is to observe recurring engineering responsibilities in public materials and compare those responsibilities with the mission framework. As you listen, notice both the overlap and the differences. The same mission may exist in several company types, but carry different business importance. Conversely, similar job titles can refer to different technical ownership. This section is most useful when combined with current job postings. Use the company type pattern as context, then verify the specific responsibilities of the role you are actually considering. Fabless and platform companies concentrate on creating differentiated silicon and the software ecosystems around it while relying on external manufacturing partners for wafer fabrication. That business model places strong emphasis on architecture, digital and analog design, verification, physical implementation, post-silicon validation, product engineering, software, and customer integration. Advanced packaging has also become increasingly important as high-performance products adopt chiplets and HBM. The important career lesson is that fabless does not mean disconnected from manufacturing. These companies still make decisions that depend on process technology, package capability, test, yield, and foundry collaboration. They simply own those relationships differently. The published roles associated with fabless and platform companies show how broad the engineering surface can be. Architecture and design remain prominent, but so do verification, silicon validation, software, product engineering, packaging, and customer-facing technical roles. Rather than treating the role list as a fixed hierarchy, use it to identify recurring ownership. A verification posting may emphasize methodology and coverage, a post-silicon role may emphasize bring-up and characterization, an applications role may emphasize customer integration. Those differences matter more than the company label. When evaluating an opportunity, compare the stated deliverables and required evidence with the corresponding mission in the framework. A memory IDM designs memory products and also owns substantial manufacturing technology. That combination creates career paths across device engineering, process integration, unit processes, equipment, metrology, yield, product engineering, test, quality, reliability, packaging, factory operations, and increasingly software and data. HBM strengthens the connection between memory design and advanced packaging, making package architecture, assembly, and multi-physics engineering more central to product differentiation. For students, this company type illustrates how one product family can support careers from semiconductor physics to factory software. The unifying theme is high-volume, high-yield manufacturing of extremely complex memory structures. Published memory IDM roles demonstrate why a single label, such as memory engineer, is too broad for career planning. Public postings separate device, process, product, application, packaging, system, software, and manufacturing responsibilities, because each requires a different form of expertise. The useful exercise is to translate those titles into engineering ownership. A process integration role coordinates a flow. A product role characterizes silicon, an application role connects the product to customer use, a packaging role solves integration problems. Seeing those distinctions helps you identify which knowledge you already possess and which bridge would be most valuable if you want to enter the memory industry. A logic IDM with foundry capability spans an unusually wide range of missions because it may design its own processors or SoCs while also developing manufacturing technology and serving external design customers. That combination brings architecture, design, verification, post-silicon validation, process integration, equipment, yield, packaging, design enablement, and customer engineering into one business ecosystem. It also makes the interfaces between missions especially visible. Design teams depend on process and PDK quality foundry customers, depend on enablement and applications, support manufacturing teams, depend on stable product and yield learning. For career exploration, this company type shows how technical depth can coexist with broad cross-functional mobility.